Hello friends, I hope you have enjoyed my lecture on band theory. Let's talk about Fermi level. What is the physical significance of Fermi level? Let's start with this question. Try to find it yourself. What will be the answer? Obviously, I will give you the answer at the end of my lecture. Now, we are in the age of semiconductor technology, say chip technology. And the electrical properties of solid state electronic devices depends on majority or minority carrier distribution in various bands. To know the carrier concentration in various bands, we obviously need a statistical approach. Now, what would be the statistical approach, the probabilistic approach? Here we are dealing with electrons, and electrons obeys FD statistics, that means Fermi-Dirac statistics. I am not going to discuss about various kinds of statistics, that is Fermi-Dirac, Maxwell-Boltzmann, Bose-Einstein. Rather, I will give you just the foundation, just the idea of FD statistics here for the sake of my lecture. In FD statistics, the particles are indistinguishable and obeys Pauli exclusion principle. Now, to give you an idea about what the Fermi-Dirac distribution function is, I should start from MB statistics. You know this formula, N2 by N1 is equals to e to the power minus of E2 minus E1 by KT, where T is the absolute temperature, K is the Boltzmann constant. N2 is the number of particles in energy level E2, N1 is the number of particles in energy level E1. So, the number of particles, what will be the number of particles in energy level E2? It depends upon the energy difference E2 minus E1. You can easily see this from this expression. So, it is the probability distribution function in case of MB statistics. Now, the question is, what would be the distribution function, probability distribution function in case of FD statistics in our case? It would be f of e is equals to 1 divided by 1 plus e to the power e minus ef by kt. I am not going to derive it. We will derive it in statistical mechanics. Now, I want to define the Fermi level. This EF is the Fermi level, energy of the Fermi level. Now, if we plot the distribution function with energy, then we will get this type of curve. I have shown you for T is equals to 0 Kelvin and for any two arbitrary temperature T2 and T1 Kelvin, where T2 is greater than T1. Now we will explain this curve. First, I want to just define what is the definition of Fermi level. What is the Fermi level? For T not is equals to 0 Kelvin, you can easily show that if I put E is equals to EF, then this distribution function becomes f of E is equals to 1 divided by 1 plus 1 is equals to half. Thus, an energy state which has a probability of half being occupied by an electron is Fermi level. This f of E, that is the distribution function, is the probability of occupation of an electron a particular energy level E. So, the Fermi level is that energy level for which the probability is half of being occupied by an electron. Now, how I have drawn this graph, I should explain it. Now, for T is equals to 0 Kelvin, you can see that if E less than EF, if E less than EF, then E to the power term is actually negative. So, f of E is equals to 1 divided by 1 plus e to the power minus infinity. You can see for T is equals to 0, E minus EF is negative, so e to the power minus infinity. E to the power minus infinity means 0. So 1 divided by 1 plus 0, that is equals to 1. So below E is equals to EF, the probability is 1. That means all the energy levels are fully occupied by electrons. And for E greater than EF, that is above the Fermi level, f of E is equals to 1 divided by 1 plus infinity. Why infinity? Now, since E is greater than EF, then E minus EF is a positive quantity and T is equals to 0. So, e to the power infinity, that is equals to infinity. So, f of E becomes 0. Thus, the probability of occupation of energy level at T is equals to 0 Kelvin greater than EF is 0. Thus, I can say at temperature higher than T is equals to 0 Kelvin, the probability. What is the definition of Fermi level at T is equals to 0 Kelvin? I should say the highest occupied energy level is the Fermi level. You can I have just explained it. Now, what would be the nature of the curve for temperature higher than T is equals to 0 Kelvin? The probability f of E exists that above Fermi level to be filled, and the probability 1 minus f of E exists that below Fermi level to be empty. Now, I should say, or you can just think of yourself that the number of electrons which get excited from the occupied level at T is equals to 0 Kelvin for E less than EF is equal to the number of electrons which becomes empty, which are getting excited from the energy levels E less than EF. That means the Fermi function must be symmetrical about EF for all temperature. Now the field energy level I have shown you here by the yellow region, and the empty energy levels I have shown here by green region. These two regions will be same. That means the Fermi function is symmetrical about EF for all temperature. This is a very important conclusion here. Remember it. Now, as an application, I want to discuss with you the position of Fermi level in case of intrinsic, p-type and n-type semiconductor. I have just shown here the EF and greater than EF, the conduction level EC, and below EF, the valence band EV. I hope you have the idea about band. Now, I just rotate the car. So, we have got a figure as you can see here. Now, with the help of these graph, I have drawn here the intrinsic, n-type, p-type semiconductor. For intrinsic semiconductor, n-type semiconductor, p-type semiconductor, the position of Fermi level. You just remember, you just watch carefully, observe carefully the violet arrows and the green shaded regions in each graph. You just observe it carefully. Don't worry, I will explain it. So, for the position, why I have drawn the position of Fermi level at the midway between the conduction band and the valence band. The position of Fermi level is in the middle of conduction band and valence band. I have just explained what is Fe. Fe is the probability of occupation of electrons of a particular energy level. Now, the concentration of electrons, that is N, and the concentration of holes, that is P, is same in conduction and valence band respectively. So, since I have told you that you should remember that the function F is symmetric about EF. So, since the probability of occupation of electrons in the conduction band is same as that of probability of occupation of holes, that is not being occupied by electron, is same, so it will be symmetric. Thus, the value half will cut the curves at the middle of the region. So the Fermi level will be in the middle of conduction band and valence band. Now what will be for n-type semiconductor? You know that for n-type semiconductor, the concentration of electrons in the conduction band is very much greater than the concentration of holes in the p-type. Concentration of holes, that means p, in the valence band. So f of EC, that means the probability of electron being occupied by the conduction band is very much greater than the probability of holes being occupied by the energy levels. So I just shown you by the shaded region by green color and by the violet arrow. If I stretch this curve, because the probability of being occupied by energy levels below valence band by electron is very less, tends to 0. So I am stretching this curve towards the conduction band. So as I stretch this curve towards conduction band, and since the distribution curve is symmetric, so the value half will cut the Fermi level towards the conduction band. I hope you can easily think over it and you can understand. Now, what will be the case in p-type semiconductor? Here, 1 minus f of EV is greater, have greater value. Why? Because the concentration of electrons in, that means N, in conduction band is less than the concentration of holes, that is P, in the valence band. So the concentration of holes which is defined by the probability 1 minus f of EV. Actually f of EV is the probability distribution function which signifies how much electrons are occupied by that energy level. So 1 minus f of EV, that is the probability of a function of a energy level EV which is not occupied by electron. That means the occupied by hole. So if value has large value, it has a large value. That means if we squeeze these curves towards the valence band, so the tails of the curve towards conduction band will getting lower to the valence band. So the value half will cross these curve very near to the valence band. So the Fermi level will be very near to the valence band. I hope you can understand these figures. Now I already asked you the question, what is the physical significance of Fermi level? I should give the answer now. I hope you have tried yourself. Fermi level is a reference energy level. Now you will ask why. The difference EC minus EF in n-type semiconductor increases the number of electrons because the f of E, the probability distribution function, increases. The value of this probability function increases as the value EC minus EF increases in case of n-type semiconductor. And the difference EF minus EV in p-type semiconductor increases the concentration of holes, that is P, because EF minus EV 1 minus f of E increases as EF minus EV increases. So at last I can say that the Fermi level is a reference energy level. That means by making it reference, what is the difference of EC minus EF? What is the difference of EF minus EV? It will depend the concentration of holes and electrons with that difference. So I should explain that it is not that kind of energy level what we have taught in our class 10 level or 10 plus 2 level. That means for say n is equals to 1 level of hydrogen atom, there are some electrons. N is equals to 2 level of hydrogen atom, there are some electrons. So is there any electron in the Fermi level? No, there may not be any electron in the Fermi level. It is just a reference level. It may happen that there are some electrons, that is, I have already told you that at T is equals to 0 Kelvin, there, that is highest occupied energy level. It may be that this is the highest occupied energy level, but it may be that it is in between the conduction band and the valence band. So EF, so that is the forbidden energy gap. So there will not be any electron. Therefore, I should say that EF, that is the Fermi level, is a reference energy level. Thank you. I hope you have enjoyed my lecture. Thank you again for patiently hearing me.